All right, what comes into your mind when I mention systems of equations? You did this in Algebra 1, you did this in Algebra 2. What comes in your mind when I say solve a system of equations? Just kind of ignore the substitution part at this point. What is a system of equations? What do we mean by this? Anybody? Somebody? System of equations. What is one?
Maybe like two equations with two different variables.
Two equations with two different variables. That's an example of a system of equations. That's exactly right. So we could be looking at, for example, 2x plus 3y equals 8. And then x minus 2y equals, let's see, what could we have there? 1 and 2, negative 3. Right, that's a system of equations. Specifically, what kind of equations are these? What kind of equations are we looking at, these two equations? Standard form of linear equations, right? So this is the standard form linear equations. Both of these are ax plus by equals c. So they're both standard form linear equations, which means their graphs are lines. All right. What would we mean if we're solving a system of equations? What is the solution going to look like? What is the solution of a system of linear equation?
X equals something, y equals something.
X equals something and y equals something. So we're going to have an x value and a y value, and what is that called? It's called an ordered pair, a coordinate, or a point. Okay? And specifically, the solution to a system of linear equations, it's the intersection, the point of intersection, the intersection point of the two graphs. And this is what's extremely important. We're looking for the point of intersection of the graphs of the two functions. Now, we're not going to get into it, but we could talk about the intersection of a parabola and a linear equation. We could have two solutions there, right? But what we're going to focus on today and tomorrow is the intersection or the solution to linear equations. And if two linear equations are going to intersect, they're going to intersect in a single point. Right? You can see how it would be impossible for two lines to cross twice unless they cross everywhere. Right? They'd have to be the same line if they share 2 points or more. All right. Now, could you think of a situation where two lines wouldn't intersect? Parallel lines would not intersect. So if we're talking about a system of equations where the lines are parallel, meaning they would have the same slope, then those particulars, that particular set of linear equations would have no intersection point, no solutions. Okay. If you have the same line, then you could say they have all points in common, or infinitely many solutions is what you've been taught in Algebra 1 and Algebra 2. All right, so this is going to be a quick review. There are, let me just kind of go through this because I want you to see it and know that what we're doing today is not comprehensive. There are several methods for solving systems of linear equations. You can solve them. You can solve systems of linear equations by graphing. And we're not going to do this just for sake of time. We're going to skip past the graphing part. But I want you to know that what we're finding is the physical location in the coordinate plane where these lines would intersect one another. And you can find that graphically using your graphing calculator or even graphing by hand. What we're going to look at today is substitution. So we can use a substitution method. We can use the elimination method, which we'll look at also today. Those are the two that we'll look at today. And then there's other methods that you probably did in Algebra 2 using matrices. I remember doing matrix operations. You did something called Kramer's rule. Does that ring a bell at all? Kramer's rule. And you can also do what is called Gaussian elimination. Gaussian elimination is tied very closely to our algebraic elimination method that we're going to do in class. We're going to focus on these two methods today in class, and then we're not going to revisit graphing, and we're not going to revisit the matrices operations. There is a class that you can take in college. I recommend you take it if you need another math class beyond college algebra and trigonometry. The class is called linear algebra. Linear algebra is deals with a lot of these matrices techniques, using matrices to solve systems of equations. All right, but today we're going to focus on solving systems of equations by substitution. Here's the method or the process, the steps in the process for solving by substitution. The problem that we have with a system of equations with two variables is we don't have any methods of solving two variable equations, right? We need to somehow get it down to one variable. If we have one variable, then we're very skilled at solving equations that only have one variable. So the first step is to solve for y or solve for x or whatever your variable may be. Solve one equation for one of the variables, and then we will substitute that value into the other equation, resulting in an equation that just has one variable in it. So if we can get rid of one of the variables, then we can solve and get a numerical answer. You would solve for that first variable, get x equals something, and then you can substitute that back into one of the original equations and solve. All right, very important because it's very easy. Always check your solution in both equations of the original system to make sure that the answer you got is correct. You can generally do this by inspection. Just kind of check and make sure that it works. If it doesn't, then you can go back and start looking for your errors. So here, first example. Solve using substitution. The two linear equations we're working with here are y equals 3x and 2x plus 4y equals 28. Y equals 3x and 2x plus 4y equals 28. Now the directions here say solve using substitution. If the directions said find the solution of this system of linear equations, then we need to kind of have these techniques in our mind so we know what we can try to use. All right, so we're solving using substitution. Step one is to get one of the variables by itself. We don't have to do that because we already have y equals 3x. It's by itself. So what's the next step? Plug what in? Plug 3x, because y is equal to 3x. We can put 3x into the place of y in the other equation. And that results in 2x plus 4 times 3x equals 28. Something that we could solve by observation as college algebra students. What is 2x plus 12x going to give us? 14x, and 14 goes into 28. 2 times. So x equals 2 is our solution, and we're halfway there. How do we know we're not finished? We have to find a point, right? So we need an x value and a y value. The solution to a system of equations is an ordered pair that satisfies both equations. It's the point of intersection. So plug that back into one of the original equations. In this case, much easier to plug it into the y equals 3x. Y equals 3 times 2. 3 times 2 is 6. All right, so x equals 2 and y equals 6. Always give your answer as an ordered pair because the solution to a system of equations is the point of intersection. So we want to give it as a point. All right, now real quickly, check that mentally. Is 6 equal to 3 times 2? Is 2 times 2 plus 4 times 6 equal to 28? 3 times 2 is 4. 4 times 6, 24. 4 plus 24 is 28. So it works. You can check it in both both systems, both equations, and it works. All right, next example, y equals 4x. And 3x plus y equals negative 21. everybody put your pencils down. Let's just kind of talk about this and see if we can power up our minds and do this mentally. Now, I wouldn't suggest that on a test, but I want you to make sure that your mental processes are sharp. If you substitute 4x into the second equation, what do you get?
-3.
3x plus 4x equals -21. So that's 7x equals -21. X equals -3, right? And y equals 4 times -3. So y equals -12. So our solution is x equals -3, y equals -12. And you can do a quick check of that. It does actually work. Okay? But the process, if we walk through there, plug 4x in, and you get 7x equals -21, x equals -3. Substitute that in, and you get x equals -12. And we were right. So this is one of those things that I want you to kind of make sure that you engage your mental processes. Now, on a problem like this one, or even on the previous one, it's really easy to do them mentally. If we run across a problem where, and again, you could check that solution and make sure it works, and it does indeed. This one, for example, is going to be a little bit more difficult to handle. 2x plus y equals 7. 3x plus 2y equals 11. Somebody know?
It's like walking back.
All right? 3x plus 2y equals 11. This one probably is not one that you could do mentally. I mean, you could, but it'd be a whole lot more work than writing it down. What is different about this problem and the previous problems?
There's nothing by itself.
We don't have y already by itself or x already by itself. We have to do that first step in the process, which is isolating one of the variables, getting one of the variables by itself. Now, is it obvious which variable we should solve for, which equation?
Yes.
Which one, Jagger?
First one and solve for y.
We should solve the first equation for y, because if we solve the other equation for either variable, or if we solve the first equation for x, we get fractions. We can handle fractions, but we don't want to if we don't have to. So the first step is to solve the first equation for y. And what will we get when we do that? Y equals negative 2x plus 7, right? Then we want to take y equals negative 2x plus 7, substitute it into the other equation. And you see the processes here probably jump past what we can safely do mentally, the average person anyway. Substitute negative 2x plus 7 into the place of y. So we get 3x plus 2 times negative 2x plus 7. And then from there we can distribute and solve for x. And we get x equals 3. Then what? Plug it in where, Garrett? One of the top equations. Does it matter? It really doesn't matter. You could plug it into any equation anywhere. And here's why it doesn't matter. Because if you made a mistake in this process, then this is going to be wrong anyway, right? And if it's wrong there and you plug it in up here, what comes out is going to be wrong no matter where you plug it in. So the important part of this process is making sure that you check your answer after all is said and done. That's the only way you can kind of really make sure that you didn't make an error. Check your answer. So plug it into the easiest place possible, which would be right there. Negative 2 times 3 is negative 6, and negative 6 plus 7 is 1. So our solution is x equals 3, y equals 1. All right, now do a quick check. 2 times 3 plus 1. What is 2 times 3 plus 1? 7. So we're good there. What is 3 times 3 plus 2 times 1? 11. So we're good there, and our solution works. And you may have, and I've told students this before, always go back to your original equation. The only time it's important to go back to your original equation is when you're checking your answer. Okay? You can use any equation along the way, whichever equation you want to substitute this value back into to find the other value. All right? So just kind of keep that in mind. So our solution here is 3, 1, and it works. And don't write this one down because I don't think you need to do it. But what's different about this problem? Ooh, you jumped methods on me. Now, explain what you mean there, Garrett.
Oh, succeed. I just remember where you get the y's and x's, or one of them equal, and then you can cancel them.
There you go. So if they're opposites, you can add the two equations together. That's the elimination method. We're going to cover that next. All right. But if we're solving this by substitution, and certainly the elimination method would be easier. What's different about this? What's different about this one than the previous ones?
You can solve for x or y.
We can solve for x or y in both equations. Does it matter?
No.
It doesn't matter, right? So we have choices in this one. In the previous problem, it was clear which one we should solve for. In this one, it's not as clear. Just choose one and go. It makes sense to solve the first equation for x or y because it's the easiest ones to do. But if you solve that way, it doesn't matter. And you do, a lot of you kind of already seen it. The solution here is 2, 8. All right? Now, everybody write this next one down because the next one is a little bit challenging. 2x plus 3y equals 6. 5x minus 2y equals negative 4. If this is a scenario where you were given a choice of methods to solve, substitution is not the way to go on this one. I'd use a different method. If you can't evade fractions in the process, then you should use elimination, which we're going to learn next. But you'll see why. But fractions are okay. We can do that. Can you see real quickly that there's no clear variable we should solve for here? We got 4 choices, and all 4 choices will lead us to fractions, right? So we can't avoid fractions. What should we do? Which one do you want to solve for? Not sure what that sound was. Which one do you want to solve for?
3y.
Solve for y in the first equation. All right, so if we take the first equation, 2x plus 3y equals 6. If we solve for y, we get 3y equals negative 2x plus 6. And then we have to divide everything by 3. Be careful. Everything gets divided by 3. And that will give us y equals negative 2/3 x plus 2. We can't avoid the fraction, but we're going to take care of the fraction. So I want to substitute that value into the other equation. So the other equation is 5x minus 2. In the place of y, I'm going to put this negative 2/3 x plus 2 equals negative 4. 5x minus 2y equals negative 4. All right. Distribute the negative 2. That'll give us 5x plus 4/3 x minus 4 equals negative 4. Now, what have I been trying to condition you guys to do all year long when a fraction shows up? Eliminate the fraction, right? By doing what? Multiplying through by the denominator or a common denominator. So that'll give us 15x plus 4x minus 12 equals negative 12. Combine those two, add 12 to both sides. We get 19x equals 0, which means x equals 0. If x is 0, if you make that substitution, x is 0 in either equation. If we zero out the x's, we got 3y equals 6, which means y equals 2. Negative 2y equals negative 4 means y equals 2. So our solution is 0, 2. And then a quick check of that will give you the solution. Confirm the solution. Right? Any questions? All right. Now, substitution is, particularly in a situation like this, involves a lot of work. And just, you've got tedious fraction work sometimes. You got to be careful with negatives and positives. The elimination method is a far easier and more efficient method to use when we're solving systems of equations. You've already hinted at it. Garrett's already hinted at it. And Holt, you solved that problem a minute ago in your head using elimination. So you guys are familiar with this process. Our goal is still the same. Get rid of one of the variables. In substitution, we did it by substituting. In elimination, we're going to do it by eliminating. Opposite values will allow us to do that. Okay? Elimination works really great in problems like this. Right? What's the solution going to be? X is 6. If X is 6, Y is 0. That's exactly right. Okay? And you can see that by elimination. Now, in elimination, instead of using substitution to eliminate a variable, we're going to get opposite coefficients. And if we have opposite coefficients, then we can add the two equations together. 2x plus x is 3x. 12 plus 6 is 18. Divide both sides by 3, and we get x equals 6. Once you know one of the values, then you can substitute that into the original equation and get 6, 0 as your solution. Now, you know that you can do this, but I want to ask you the question, why? Right? Algebra is learning the skills, learning the rules that we can use to solve all types of equations. Why are we allowed to take these two equations as they're given to us and add them together? Would that be something that you would think we should add the two equations together? It's a reflex that you have to kind of condition. Why are we allowed to do it? What are some things we're allowed to do to equations? They have the same variables. We would need them to. That's a condition that would need to be met. But we could add them together even if they didn't. It wouldn't get us anywhere, but we could still add them together. What are the rules? You just taking a little walk?
Yeah, I just need to walk around.
All right. What are the rules? What are we allowed to do in solving equations? Todd? Anything? Engaged? Anybody want to engage here? What are we allowed to do if we're solving an equation? Here's an equation.
Multiply everything.
We're allowed to multiply everything.
Oh, wait. Okay, I know.
All right? We're allowed to multiply everything, and Jagger thinks he knows why we're allowed to add these two things together. What else are we allowed to do to equations? We're allowed to... I'm not going to give it to you. I'm going to make you think. I'm going to make y'all wake up from this lunch fog. What are we allowed to do to that equation?
Solve it.
How? Subtract 3 from both sides. So we're allowed to subtract the same value from both sides. We're allowed to add the same value to both sides. We're allowed to multiply both sides. We're allowed to swap sides of an equation. That's about it, right? That's the addition property of equality, the subtraction property of equality, the multiplication and division property of equality, and the symmetric property of equality. All right? So the reason we're allowed to add these two equations together is because they're both equal. So when you add these two equations, you're adding equal values to both sides of both equations. And that's why we're allowed to add two equations, because they're equal to each other. It's the addition property of equality that allows us to add these two equations together to eliminate one of the variables. And there we have y equals 0, x equals 6, y equals 0. All right? What about this one? We got to multiply something, right? We could multiply the second equation by 2 and eliminate the y's, right? Or we could multiply one of the equations by -1 and eliminate the x values. So again, we're using two properties of equality. The multiplicative property of equality says we can multiply any equation by anything we want to. And then the addition property of equality gives us permission to add these two equations together. So let's just change the signs. Let's go through the second equation and change all the signs. So it'll be negative 3x, positive y, negative 10. Add the two equations together and eliminate the x's. Then we get y equals 2. Substitute that in and we get x equals 4. And that's pretty easy. So if we're given opposites, we can just add the two equations together as they are. If we can change all the signs and make opposites, that we can do that. All right? And as Garrett said, we could have also, what's your question, Garrett?
Never mind. You'll probably get to it later.
Is it?
Yeah, just keep going.
As he said, we could have multiplied the bottom equation by 2 and eliminated the y's, and we've been good there. All right? So we can multiply and get rid of a variable. So in this problem, because we can eliminate x or y, how would we eliminate x? Multiply the top by negative 3, right? The entire equation, the top, we multiply by negative 3. How would we eliminate the y's? Multiply the bottom equation by not negative 2. It needs to be positive 2 because we don't need to change the sign, right? So that's the choices. I think that the PowerPoint's going to take care of the x's. And this is how I suggest you do that. If you have to multiply one of the equations, kind of carry them both over to the side. Keep them lined up, x and y's, so that it looks something like that. Good solid processes. Don't do this stuff mentally and write stuff. Show your processes so you can check your work, find errors. All right, now we're ready to eliminate. Negative 3x, positive 3x is gone. Negative 12, negative 2 is negative 14y. So negative 14y equals negative 42, which means y equals positive 3. All right. Substitute that into one of the given equations. X equals 5 and y equals 3. Go back to your original equation and check. Let's make sure this works. If we go back to this original equation here, is 5 plus 4 times 3 equal to 17. 5 plus 4 times 3. It's 5 plus 12, right? All right, the second one. What about 3 times 5? What would that be? Minus 2 times 3. 6. 15 minus 6 is 9, so we get 9 equals 9, and it checks in both situations. All right, so the final scenario, last example. 2x plus 3y equals 6. 3x minus 4y equals negative 25. How would we eliminate x in this one? Top by negative 3, bottom by 2. Are we allowed to do that?
That's what my question is.
Yeah, we are. We're allowed to multiply as long as we multiply through an entire equation. Let's just take that suggestion and run through this. If we multiply the top equation by negative 3, what will that give us? Negative 6x minus 9y. Go ahead. Negative 18. Multiply the bottom equation by 2, and that will give us positive 6x minus 8y negative 50. All right? We can eliminate the x's. Negative 17y equals negative 68. Y equals 4. All right, make that substitution now. Y equals 4. Let's use this equation right here. It's got positives in it. 2x plus 3 times 4 equals 6. Subtract 12 from both sides. 2x equals negative 6. X equals negative 3 when y is 4. Okay?
Yeah.
Got it? So substitution and elimination. Again, you saw this in Algebra 1, you saw this in Algebra 2, and now you're seeing it again in college algebra. Your homework. I want you to work these problems, these first problems here by, I think the directions are there for you, by substitution, 20 through 30 even. Work those by elimination. Now, 1 through 4, it's just asking you to check the answer that's given to see if it's a solution or not. All right, it's not asking you to solve, it's just asking you to confirm whether it's a solution or not. Any questions?